All right, today we're going to dive into one of the most fundamental forces in the entire universe, radioactivity. It's this invisible energy that's all around us, constantly shaping our world, from the fiery heart of a star to the very atoms inside you and me. So how can this one unseen force hold the power to both create and to destroy? Well, let's get into it.
Think about it. It is a force of incredible paradox. It can heal us, but it can also harm us. It can tell us about the ancient past, and it can power our future. So how on earth can a single process be responsible for things that are so wildly different? That is the central question we're going to unravel right now.
And you can see that paradox laid out right here. On one side of the coin, it's this incredibly precise tool for medicine, a key that unlocks ancient history. But you flip that coin over, and it's a source of unimaginable destruction and biological danger. You really can't understand radioactivity without understanding this deep, fundamental duality.
Okay, to get to the bottom of this, we need to think small, like really, really small. We're about to go inside the atom itself to find the very source of this incredible power.
It all starts right here, in the nucleus. This tiny, unbelievably dense core is just packed with protons and neutrons. A good way to think about it is like a tightly wound spring, just humming with an immense amount of potential energy.
But here's the catch. The stability of that nucleus, whether it's calm or not, depends on this super delicate balance, the ratio of neutrons to protons. You see, all those positively charged protons are desperately trying to fly apart from each other. The neutrons, they're like the cosmic glue trying to hold the whole thing together. And when that ratio gets out of whack, the nucleus becomes unstable. It's suddenly holding way too much energy, and it has to get rid of it, like right now.
And that urgent release of energy, that is what we call radioactivity. It's the natural, spontaneous process of an unstable nucleus just breaking down, or decaying, to try and find a more stable, calmer state. And here's the key. It's not something we can start or stop. It's a fundamental process of nature itself.
And this isn't just some abstract idea, As you can see from this page from a physicist's real notebook, this whole process is governed by precise, predictable mathematical laws. This is the actual science that lets us understand, predict, and ultimately harness this incredible power.
So when an atom decays, how does it actually release all that pent-up energy? Well, it sends out these little messengers, or emissaries, in the form of particles or waves. There are three main types, and each one has its own unique personality. First up, you've got the alpha particle. I love this nickname for it, the heavyweight brawler. It's big, it's heavy, made of 2 protons and 2 neutrons. It does a ton of damage in a very short range because it's so highly ionizing, but the trade-off is it's actually pretty easy to stop. Next up is the beta particle, our speed demon. Now this is a tiny, super fast-moving electron. It's way lighter and quicker than an alpha particle, and that lets it travel farther and punch more deeply into materials. And finally, there's the gamma ray, the stealthy ghost. Now this one's a game changer. It's not a particle at all. It's a pure wave of high-energy light. Since it has no mass and no charge, it just slips through matter like it's not even there, which makes it incredibly difficult to block. Looking at this comparison, you can really see the trade-offs, right? Notice that inverse relationship. The alpha particle has super high ionizing power. That's its ability to knock electrons off other atoms, but its penetrating power is super low. Then you go all the way to the other end, and the gamma ray is a weak ionizer, but it can penetrate almost anything. And that difference, well, it's everything when it comes to how we use them and how we protect ourselves from them.
So what does this mean in the real world? It's pretty striking. That big alpha brawler can be stopped cold by a single piece of paper, or even just the top layer of your skin. To block the beta speed demon, you're going to need a sheet of aluminum. But to stop that gamma ghost, you need thick, dense stuff like lead or solid concrete.
So here's something amazing. While the decay of any single atom is totally random, when you get a huge group of them together, their collective decay becomes incredibly predictable. And that predictability gives us a way to measure the invisible. It's like an atomic clock ticking away at the very heart of matter. This atomic clock runs on a concept called half-life. It's simply the precise amount of time it takes for exactly half of a radioactive sample to decay. This isn't a theory or a suggestion, it's a physical constant. And what's really mind-bending is the range of these half-lives. Some are over in the blink of an eye, just fractions of a second, while others, like for uranium-238, last for 4.5 billion years. That's about the age of the Earth itself. And the process itself
is just beautifully predictable. After one half-life goes by, 50% of the original stuff is left. After a second half-life, you're down to 25%. This perfect exponential decay means that no matter how much you start with, the rate is always constant. And that constancy, that's the whole key.
So why does this matter so much? Because this atomic clock is literally how we date the past. By measuring the amount of carbon-14 left in, say, an ancient bone or a piece of wood, scientists can calculate almost precisely how long ago it died. It's just an incredible window into our history. Okay, so we've seen what radioactivity is and how it works. Now we come to the final and maybe most important question. How do we actually use it? It's time to weigh the benefits against the very real risks of this invisible force.
And the applications we've come up with are just astounding. In medicine, we use precisely aimed radiation to destroy cancer cells or tracers to help diagnose diseases. In industry, it's used for quality control, checking for leaks. And of course, as we just saw, it unlocks the secrets of archaeology.
But the dangers are just as real. Uncontrolled exposure can damage our DNA, which can cause cancer and genetic mutations. High doses are lethal, full stop. And of course, this is the very same force that gives nuclear weapons their absolutely devastating power. And this, right here, is what makes it so relentless. This quote from the source material really gets to the heart of it. You can't speed it up, you can't slow it down, you can't turn it off. Radioactive decay is a fundamental process of the universe, and it operates completely on its own terms.
So, in the end, radioactivity isn't good or evil. It's just a powerful, natural force, a true double-edged sword. Our greatest challenge and our greatest opportunity is figuring out how to wield this immense power with the wisdom and respect it absolutely demands. The choice of how we use this fundamental cosmic energy, that is what will continue to define our future.